Welcome, Happy New Year. Today we're switching on a new topic. So far we mostly focus on computer vision and images and convolution, vast normalization ResNets. Today we're moving on in a different topic, which is natural language, and we'll go into one of the most critical components for the success in recent years in natural language processing, which is the infamous transformer architecture. And we'll get to that bit by bit. I assume there's no prior knowledge on the topic, so we'll build up the concept one by one. But first, let's look a bit broader in the domain. So now we're dealing with natural language. What is a natural language? It's a language, the spoken language, or even sign language to some extent, which is represented with sentences or characters and words. And it's what humans use to communicate with each other. So in terms of a difference, it's a different input signal compared to images, which are like pictures captured from a light sensor over these three different channels intensities.
Sorry,
yes?
Are you recording?
Yes, we're recording. So there are four very fundamental differences in terms of natural language as an input signal. So first, words are not discrete symbols. What do we mean by discrete symbols? You're right to ask this question. So let's consider the task of image classification, which we have seen in various exercises so far. We have a vocabulary of 10 classes, let's say 10 images like cipher 10, and we have this label data, so we know which images correspond to one of these 10 classes, which is our vocabulary, and we represent each word as this one hot encoding, if you remember. So given that we have n classes, we represent labels, words, in this way. So we kind of discretize the language to use it as a target on image classification, to some extent. And in the 60s and 70s and maybe 90s, people tried to do these kind of things with natural language to develop natural language models. And this didn't work because words vastly different in terms of the meaning of their words. We'll get into some examples. First, how we interpret these words as humans depends on the context. The context is the social occasion, the sentence, who we're talking about. And a third and very important topic, which was addressed with this transformer architecture and attention. One of the main idiosyncrasies of natural language is that the interactions are highly global. So what we call as non-local interactions, and this is in contrast to computer vision, to images, where we're trying to leverage this locality idea that pixels that are in similar position in this two-dimensional grid have this shared semantics kind of label, if you like. And of course, we have a lot of top-down influences. When we talk about language as humans, we inject a lot of prior knowledge about our understanding of the world. We have a lot of underlying understanding concepts. Let's see some examples. So here we have the same word up and down highlighted with this red square. And after taking some time, depends if you're a native speaker or not, in the first example, you identify this character as W, so Jack and Jill went up the hill. While in the second example, you kind of get to the context that we are not using the same word went, but we're using the word event. So this is how we disambiguate language. Here is specific with the characters based on the context. A second example is, imagine I'm giving you the sentence, the cat who beat the dog barked. This is a very confusing sentence for many reasons. We don't know if it's the cat that barked or the dog. I mean, we know because we are humans, but it's really complicated in terms of teaching this in a machine learning model. So in this example, it's a very illustrative example to indicate that humans use a lot of prior knowledge, so we are kind of frequently seeing dogs barking. So when we see these two words together, the dog and barking, we kind of tend to believe, based on prior knowledge and this common frequency, that we hear dogs barking, but cats can also bark. Another example is when I present to you the same word, red, with two different nouns. So in the first example, I'm showing you a picture of, actually I'm telling you to imagine a picture of a red wine. And one picture might look like the one on the left, as you see the screen. While some might imagine that this would look like more dark color, or blackish, if you like. While in the second example, we have a picture of a red pen. I'm telling you to imagine a picture of a red pen, and it's really unlikely you would imagine the picture on the right. So as humans, in our brains, we have some internal representations of words, and based on what is in the context, we interpret those words in a different way. That's why this treating words as discrete symbols is not working in terms of machine and deep learning. I hope you develop some intuition regarding that. Here are another very good example. If I ask you to imagine, if I tell you that I ate fish yesterday, you would never imagine the picture on the left, and you would probably imagine the picture on the right. And if I told you that I have a pet at home, that's a fish, you'd probably imagine this picture something closer to the picture on the left. So this is a very short introduction to kind of illustrate the initial 4 points that I would like you to have into perspective about natural language and why it's different from other type of input signals like audio, images, and stuff like that. Any questions so far? Okay, nice. So based on that, we cannot represent as language as discrete symbols, so we need another type of representation. So the answer to this question, after many years of research in the 80s and maybe 70s or 90s, is that a very handy representation of words is to represent words as d or n-dimensional vectors that live in a feature space. And these would ideally, of course, we start from some random vector representation, but with deep learning, we learn that we can optimize our representations if they are vectors, for example, using backpropagation. So by we introduce a more flexible way, if you like, to represent language, because now words live in this high dimensional space and are free to move in a way that it optimizes a certain problem. So here in a low dimensional, two-dimensional representation, you would see that dogs and cats would be closer in this we allow after training the model, and since backpropagation enables these vectors to freely move into space, we would expect that these vectors with some similar characteristics, some type of characteristics, in this example animals or pets versus wild animals, would be clustered, grouped together in this space. And this is only achievable because we can modify this representation with backpropagation. It's not something that comes for free. So we usually use the word embedding. I would like you to remember this word. So we freely enable vectors to have different semantics on this Euclidean space, for example. And if we have a Euclidean space, we can compute cosine similarities to see how one word is close to another. And of course, this is not possible with the representation we use to train image classifier. So another famous concept is called tokenization. So far, I assume that we have a sentence, and I am chunking, I'm splitting the sentence into words, but I automatically assume that we tokenize, let's say, the sentence in terms of words, but this is not necessary. So one of the amazing after effects of the transformer is that as long as you have an input domain and you are able to find a very nice way to tokenize your inputs in a meaningful way, it doesn't matter if you have audio, depth signal, vision, or natural language, or even proteins. As long as you can define a tokenized version, a tokenization process to split your input in a specific way, you can use the transformer on top. We'll see how we do that. So recent research of the last 6 to 7 years shows that the best way to represent natural language is if we take distinct words. Another idea would be to use, for example, sentences for, let's say, a book, or we could use characters. So it really depends on the application. But this is an important concept, and I want you to remember that as long as you can create a very good tokenization of your input domain, you can use the transformer with any type of input domains, like audio, time series, sound. Next, instead of presenting it afterwards, I prefer to show it before. We have a new type of layer normalization. This was actually developed concurrently to path normalization we saw on convolutional neural networks and residents. And here we're trying to be independent of the mini-path dimension, so that because the limitation when you are taking the average, there are two problems when you're using the BATs to compute this means and standard deviation. So the first is that you mix the statistics of different images or sentences when you subtract with this mean that is computed based on the BATs. And the second is that for this accurate estimation of the means and standard deviation, you need a very large BAT size. So clarify. Can you see those on the back? All right. What I mean by that is that this computation of m, or mu as you say in English, this non-capital N, and this is D. What I haven't said is that we always consider the case where X is the input signal, and it always has three dimensions. The first is the bud size, the second is the sequence length. I use the symbol N, some papers use the symbol L. And the last one is this D dimension. So here, this is the mini buds notation that we have these kind of buds all the time. This is the sequence length. So it's so we have a sentence, and each element or token in this sentence. So let's say we have a sentence of 20 words. Then this means that n, since we tokenize, we take each word as an independent representation. N is the length, the words in the sentence. All right? And each word is represented by a d-dimensional vector, which we call D. And in terms of, if you plan to read this attention is all you need paper, which I highly suggest you do, they use this D model as the, yes?
Sorry, I didn't get what N is. N is not the number of tokens in a sentence?
Yes, it's the number of tokens. Width is the number of words, because we say that each element, each token is a word. But if we consider characters, it's the number of characters.
And then it's the length of word, or it's characters.
No, if we consider characters, and let's say the sentence has 200 characters, then this is 200. If it has 10 words, then this is 10, and we use, so we stay in the word notation for natural language, because this is like 95% of the case. So you can compute the standard deviation similarly. Oh, here I'm missing something. All that is just to say that we're not taking an average over the bud dimension. So this is, any questions regarding layer normalization? I will upload the slides. Yes?
Can you explain in simple terms why we don't use batch normalization in this case? So batch normalization would be...
batch normalization
would go on the other axis, right?
Yes, it would go, if the mini buds dimension, it would be colored in this dark blue, and the channel dimension would not be colored. So compared to computer vision, we have this, if you like, these feature maps, which are this channel C. So each channel, we said that it's intuitively a filter, and we want each filter to have a distinct representation. What we said about one is maybe a vertical edge detector or a horizontal edge detector, or if we have human faces and eye detector, and we don't want to fuse this information. But in language, it seems that we want exactly the opposite thing. So we want to fuse information from words that are, this n is the dimension of words, if you remember. So we want to fuse information from words that belong in the same sentence. This makes sense, right? Does that answer your question?
Yes.
All right. Any other question regarding normalization? All right. So we are kind of building individual components step by step, and then we will use them all together. So the next thing is a very smart, but at the same time very tricky concept to grasp. It's called positional encodings. What I have hidden from you is that when we use this process called tokenization, that take each word as a token, as a distinct representation, then I'm not dealing with a sentence anymore, but I'm dealing with a set. So in principle, transformers, in general, this approach of tokenizing the input, it completely ignores the order that these words are structured. So in mathematics, we use this it's called sets. And sets are, by definition, invariant of the order. It's called permutation invariance. It means that you can swap the elements in any way you like. It doesn't change the set. And the intuition here is that for many years, we believe that if we have machine learning models that respect this order, was the best way to learn representations and solve natural language tasks. And this is what we used to do with recurrent neural networks. We respect the order of the words, and we sequentially predict whatever we want. We sequentially process the elements by respecting the word order, but limiting ourselves to process these elements one by one. So transformers assume, this is a very, very important assumption, because there is not, as we call it, a Panagia, a tool that solves all the problems. So the transformer makes a very, very strong assumption that in your problem, in your domain, all these n elements, tokens, whatever that is, are available in advance. Can you imagine a problem where the whole sequence is not known in advance? You can imagine, for example, robotic applications where at each point in time you get a different position, or time series like the prices of the stock market. They change all the time. And that's why transformer cannot be applied to just any domain. We assume that we know in advance the length and the elements of the whole sequence. And as I said, we ignore the order and just process them all together. Any questions so far? So positional encodings is a smart trick to integrate some notion of order inside the transformer. Okay, how do we do that? Let's say we have these equations, right? So there are three things, if I'm not mistaken, that are changing. So if you imagine a matrix where the rows represent the different words, n. So this is the, I think, I. Yes. So this is the I. Let's check again. No, this is the O index, and this is the I index in the equation that you see on the slides. So if you imagine a series of words representing different rows, we want each word to have a slightly different representation, vector, a different vector in the end, that the model would ideally take into account to understand that based on the position, so the order in the sentence, it might mean something different. So let's say in the example where the word is in the first place, maybe does not correspond to the same thing if the word is in the last or in the middle. So the same word embedding, the same representation of the word can change based on where it appears in the sentence. Is that clear? And a second thing is that we also vary, we have this d-dimensional representation, and we vary, we also change by some slight amount, we change this value in the d model dimension, in the Euclidean space that this word lives, if you like. And another thing is that we vary between odd and even words. This is what these two equations essentially mean. So we change these individual values slightly different based on if they are odd or even in terms of the order. So essentially, if you have a wavelength of lambda, so if you take I equals 1, you have a very small lambda, or very high frequency if you like. And the second dimension in this d-dimensional Euclidean space, we have an I equals 2, which would result in a wavelength that is, so if you check the equation, the first one, can somebody imagine what is the connection between lambda 2 and lambda 1? Maybe? Here there is missing a scalar. So it's this 2i, so here I, which is the embedding dimension, is changing. So here we would have 2 times I, so 4, and for I equals 4, we would have 8 times. So the graph is not 100% illustrative, but you get the point. So as we go higher, like further and further and reaching the model, we are increasing the wavelength, or otherwise decreasing the frequency. And if you want to just cross-check, I think I have the numbers somewhere. F of position, I use the same notation. If we have this function, then this k is equal to 2 divided by pi, or if you prefer the frequencies, so you can solve this k, which is this 1 divided by 10,000 to this power, and you can see that how I infer these wavelengths. Is that clear? Any questions? Okay. So you will need to implement this in the current exercise. So it's just to understand that there are three fundamental. Yes.
I have a question. So the term in the sine or cosine function is the wavelength, right? Or is this basically the coefficient for the wavelength?
No, it's the wavelength. The coefficient, let's say it's 1.
Okay. So then if I'm not sure if the I goes up, then the overall term.
Yeah, I goes from.
Yeah, it goes over the d mod from 0 to d mod. Okay.
Yes.
And then if it goes up, then the wavelength gets
Ah.
lower, right? Or higher? Lower, doesn't it?
Okay, let me replace this. So this is 1, 2, 9, 10, 2 divided the model. So here it's not very well shown on the screen. So if you solve this, do you agree on that? Yes?
Where does the 10,000 comes from? Is this a random?
Yes, it's kind of hyperparameter. They define it basically it influences the, let's say if you put I equals 0, it influences the initial, let's say the first frequency or wavelength. One moment, do we agree that as I increases toward the model you get a higher wavelength? Okay. Yes?
So what is the value chosen in the original paper?
Yes, this is the proposed value.
Thank you.
So do we all agree that the wavelength is changing as we are moving towards the embedding dimension D, the model, whatever? Okay. Okay, just a small recap because it's a very tricky thing to grasp in the beginning. So we have sine and cosine is the first fundamental difference, whether we are dealing with odd or even I or n. Whether we are dealing with odd or even n or positions. The second thing is that the wavelength is increasing as we increase the embedding dimension. And yeah, let's stay here. So far we've covered tokenization, layer normalization, and positional encodings. There is, yes?
One question regarding this, why do we not just, so it's probably an idea behind it, but why don't we just use like an identity matrix and then with some columns that are just 0, so, or in your direction like this, and then so that we have every position. Like why do we make it so complicated?
Because we want to this is like this would result, this positional encodings would result in a vector, and this vector will be added, and so simple addition into the word embedding. So we are slightly modifying the word embedding in such a way to take some notion of, we inject some notion of order, because as I said about the sets and this permutation invariance thing that
because I imagine that when the I gets larger, the wavelengths are probably almost 0, and then so the probably second half, or depends on the model how large it is, but it's probably redundant. So the first part is probably interesting, and then but couldn't we just like put a 1 in for the next one, and then like a lot of identity vectors?
yeah, but in the end we want a vector in the end.
So that's the idea. So I would make a matrix and then make it here 1, 1, 1, 1, 1, 1, everything at 0, and then edit or.
You like one hot kind of encoding
yes,
for
one
each
encoding.
position.
Yes.
short answer is that it looks like this strategy works, and it looks like that the position is more complicated than just indicating the one-hot encoding of the position. Of course, this is more sophisticated. But there is no theoretical justification for this. They just propose it without any theory supporting this. In later years, somebody proposed to just pass a vector, which would be trained weights that are layered with backpropagation. This is like the next level, if you like, but many people are also using this type of encoding. It's kind of a hack, if you like, but it works, that's for sure. So the next component that we need, so any questions about the presentation so far? Okay, so the next component that we need to, like the last maybe piece of the puzzle, is this idea of feature or content-based lookup. And for that, we'll take an example with YouTube search. So let's say you want to find a YouTube video of a video you are interested to watch. Let's say whatever, neuroscience, your favorite singer, whatever. So in the search, you write in language, probably English, and YouTube has a database, so it will compare your query, so the thing that you ask for, the title. You will probably type the title of the video, and internally, under the hood, YouTube would probably try to find the best match to all the titles, the metadata, if you like, of all the existing videos that exist in this database. But in the end, what you're actually interested is the video, not the title of the video. So you can create an analogy in your mind. These are like one of the most fundamental principles in retrieval systems from the 90s. So this idea of keys, queries, and values, as it's shown in the slides, queries is what we are searching for. In the example, what we are trying to find. So I provide this title of the video that I'm interested. Keys are kind of the bridge between what you are searching and what you want to get. So let's say the title of the video in a very simplistic, simple, let's say, database implementation of YouTube. And the values is what I'm actually desiring, what I want to get in the end. So the YouTube video. Nonetheless, it's very important to highlight that we have three different distinct representations. And here I have another example that the keys and the values are kind of colored to indicate that they belong to the database. So what I have learned from previous more in the machine learning context is what I have already learned, what my database looks like, while the query is what I'm asking for. And now we make a distinction of two different things. So self-attention learns these three distinct representations from the same input signal, from the same sentence, if you like, or the mini batch of sentences, because we are having these three dimensions. Cross-attention is when the query comes from a different input signal than the keys and the values, and it's it's like one of the core innovations in language translation. So keys and values are some sort of representation / information from the language we want to translate something, and query would be the language that I'm translating from. So let's say we can input the query, which would be a sentence in English, and we want to translate it in another language, which would be Spanish or French or whatever. So these are the principles. This is a visualization. The order should have been before. This is the matrix that I tried to show before for the positional encoding. So now we are ready to see how this self-attention mechanism works. So we have self-attention. We are only looking in a mini batch of a bunch of sentences with a bunch of words. So again, we have this input vector, and we define 3 linear projections of the same input. So analogously to the information retrieval systems, so these 3 are the weight matrices, what I'm trying to, in the end I'm going to learn with backpropagation. And let's assume that these dimensions are all the same. So for simplicity, we assume that note that here I have the output vectors, or the output tensors, if you want to be precise. While I will just write for WQ. Okay, we ignore the bad size here. D model, which is the input representation, times, dk. And similarly, the same dimension dk is the same for all 3 linear projections of the same sequence. Next, we will write the formula for the self-attention mechanism. So SA is for self-attention. So this is a matrix multiplication after the softmax V. And that's it, you have the self-attention operation. So let's see what it looks like. So this is the database search I talked about. We multiply all the queries with all the keys. So we see how all this query representation maps to these different keys with this similarity computation. Another thing is it's really worth noting the dimension of this multiplication. Can somebody tell me what is the dimension of this matrix? We have QK. These are the dimensions. We ignore the bad sides. Alright, that will help. So n squared. Do we agree? So each element in this matrix, we have a square matrix. And each element in this matrix indicates the similarity between query I and Pj. So we know this is a kind of parallelization that's happening inside the matrix multiplication. So each query is a representation of a word. So we see how all the words in the current sentence are, how similar and how relevant they are compared to all the other words in the sentence. In the example of the dog barking, as humans, because of our prior beliefs and understanding of the world, we kind of think that the dog was the one that barks, if you remember this example. So we kind of, if you like, assign a higher weight, higher attention to this correlation, this similarity between dog and bark, and we assign a much lower probability, similarity, whatever. It's the same as we will see because we will apply software. Compared to the cat barking. That's why I really like this example. So, given a sentence, we see like a pairwise similarity of all these words in the sentence, how they relate to each other. And then in the next step, we take softmax, which gives us a probability distribution. So I have another illustration for that. This usually helps a lot of students understanding. So in part, this attention matrix, this 4 by 5, I have a different size of queries and values, queries and keys here. So this element A11 is just a dot product. So the matrix is a bunch of dot products together. And then we take the softmax. For the softmax, if you remember, we need the dimension. So we take the softmax over the rows in this illustration. So this gives us a probability distribution, how the query corresponds to all our existing keys. And in the YouTube video example, we want to retrieve the video with the highest similarity with the title of the query and the key. So this is a more soft way of attending because we have a probability distribution, while in the YouTube example, you need to pick one video or a bunch of videos. And then there is another multiplication happening with V, the green matrix, which is here. And this is the attention operation. Nothing more, nothing less. Any questions? Yes?
Why can keys and queries and values have different sizes?
Yeah, so keys and values need to have exactly the same number of elements. But the queries can have an arbitrary number of elements, as we said in the example of language translation. So if you see the matrix multiplication, it is the the D model needs to be the same, the embedding dimension. So we need to live with all these vectors, live in a shared embedding space. But if keys and values represent, let's say, all the information and features that need for a language translation in English, and query is a sentence in whatever French, Spanish, there is nothing in the math that restricts to have the same length. That's why in this example I wanted to illustrate this point, and I created different dimensions on purpose. But if we're talking about self-attention, of course all these three have the same length, because all these three are just linear projections of the input which have a fixed length, so a sentence of 5 words. So now we're going to the next part, which is the multi-head self-attention. So this all-to-all similarity is a type of parallelization. In one matrix multiplication, we see how all elements correlate to all other elements in the same sentence. But now we will introduce a second type of parallelization, if you like, which kind of distributes the computation that we already did, the exact same computation, in multiple parallel and distributed steps. So we introduce an index. So instead of having one matrix, one triplet of matrices, Q, K, and V, or specifically, correctly, this triplet of W, Q, K, V, we introduce multiple of those triplets. And let's say in the first example, let's say we have 2 triplets of weights. Here in the image I have 3. So we apply, let's say in this example we have three triplets, and we apply this operation 3 times. How much more expensive is to do that? If it's if B of K is the same on all these 3 operations, we have a 3 times more complex operation. Do we agree on that? But what do we gain? We gain that we allow a word to have different interpretations, different representations, different, let's say, internal embeddings, if you like. We allow the word to have multiple meanings, as we described in the example of natural language. So one time the fish can be a pet, and another time the fish can be something that you get for lunch or dinner. Do you get the intuition why we introduce this kind of distinct, another set of distinct representations? Do you want to ask something?
Yeah, what hinders two heads to have to be the same? I mean, they're probably initialized a little bit different, but could they be the same?
The difference comes from random initialization and backpropagation. So they will update it in a completely different, with different gradients, because we compute the partial derivatives for each of these triplet of weights. But of course, if you initialize them with the same values, they will have the same partial derivatives. So you need to initialize them with different values. And it's the same thing that different convolutional we have this channel dimension, and these channels would capture different features of the same image, if you like. The problem is the computational complexity. So in this example with 3 heads, we have 3 times the amount of complexity. So what is the simplest solution? Let's reduce this dimension to 8, where 8 is the number of heads times k. So if we have 500 here, and we have 5 heads, instead of, if we have single head attention, this h equals 1, so the d model and dk are the same dimensions. And as we design the model with more and more heads, we reduce this dimensionality here, this dk. This is the internal dimension where all the weights follow. So by this way, we introduce minimal overhead over having one head. Do we agree on that? Okay, I haven't told you about where the overhead comes from. So then we just concatenate all the outputs and pass them from another linear layer. And this is the only overhead which is insignificant compared to the amount. And another thing we kind of gain for free is that this process can be parallelized. So here, if you see with the red, I have tried different workers. It can be a GPU, TPU, whatever you might have, or different CPU cores, whatever. And this is something that we gain, let's say, for free, while allowing the model to capture multiple representations of the same sentence, because we explain this this interaction in natural language where the word depends on the context. So we are allowing, for example, the word. There are many cases where the words, as humans, we use words that have the exact same word can have two different meanings. Let me think, which is an example of that. For example, in Spanish, you can use the word banco to indicate the bench, or you can use the word banco for the bank. So in this way, you can imagine that we allow the model in a way to capture different representations. And this WO is the last matrix, just another linear layer that just after the concatenation, it brings you back to the D model dimension. So there are two things. So here we have a transformer block, multi-head self-attention. The input is X, and the size is bat size, sequence length, dimension. Okay, D model. A very nice thing is that the shape, the dimension of the tensor is not altered during one multi-head self-attention block. So let's see, are there any questions about multi-head attention so far? Something you would like to discuss again? Yes?
Yeah, you said E model is H times K. Doesn't mean we...
This is the number of heads it can be...
Yes, and the D model is the embedding length, right? So...
Yes, let's say we decide that all words live in a 512 dimensional space.
Okay, so if we have like two heads, then we would split them, right, like 256.
Yes, then
we would split one embedding, one word basically, and...
No, we would not split it, we would project from 512 dimensions. We would project the word from 512 to some WQ, WK, WB. So we would have 256 3 times. and then this would be the first head and the second head. So we project the input dimension into dk. It's like usually, let's say, because it's never higher, so it's usually a lower dimensional representation of this word. And then we allow for multiple types of these triplets. So typically, I think it's like 8 heads minimum, and this is one of the most critical factors to achieve high performance in natural language translation. So if this is 512, we project in a 64-dimensional space of these key squeeze and values, but we can have a bunch of them, so 8 triplets. Is that clear? Okay. Yeah. So another thing I haven't covered, and one thing that I haven't covered, and it's quite crucial, is this division here, this scaling down by this scalar called dk, which is the dimension that we project, as your colleague mentioned. So with this square root of dk, with this scaling down, if you like, because dk is always like an integer higher than 1. we enable, let's say, stable training. They write something like this if you read papers regarding the transformer architecture, or blog post, or whatever. So I want to give you some small intuition regarding that. So do we agree that we have a dot product? So each element of this Q divided by K is a dot product operation. Let's say whatever. So the problem with these dot products is that they can get arbitrarily large. And this is problematic. Why? Because we have a softmax operation that is applied afterwards. And the purpose of the softmax is to create this probability distribution, as we said. So even though we cannot visualize softmax in a high-dimensional space, in the two-dimensional space, softmax looks like the sigmoid function, which is more or less like this, where here is 0.5. So this is kind of an individual, looking at softmax in one of the individual dimensions where we apply softmax. So in this example, if we apply softmax over the rows of this attention matrix, which is 4 by 5, we have these 5 different dimensions. So in one of those dimensions, intuitively, softmax looks like a sigmoid. And the issue is that as this dot product gets arbitrarily large, so arbitrarily high or arbitrarily low, we get outside of this area here. We go into these regions where we have this, the function saturates. So it looks like, if we exclude this part, it looks like a step function. So it's either outputting 0 on the y-axis, we get either 0 or 1. So it looks like a step function, and the gradients saturate. So if you take the gradient here, the gradient is 0, which is something that we really don't want, since we are going to compute partial derivatives and apply backpropagation, and we're going to learn all these amazing representations for each word. So this division here is avoiding the dot product to become arbitrarily large, and it keeps all the gradients in this range where the output doesn't look like step function, but it's more like continuously going from 0 to 1. So regarding that, there is a proof. Okay, actually there's no proof, but the paper, the famous paper that proposes architecture, is called "Attention is all you need." They make a statement which they don't prove, but we will. Just to showcase this, the example of this saturation I have explained. So for those who want to refresh their knowledge on probability distribution and statistics, here I have, we will need these two properties. So the first one is when you have an expected value, which is a mean, and a sum, you can take the sum outside, and this is one way to compute the variance. So we assume that all the elements of Qi, where Q Pk. So we have these vectors, query and keys, and all the elements are independent random variables with a mean of 0 and a variance of 1. So what we care about is not the individual means and variances, but what happens with the mean and variance of the dot product. So we want to investigate, given two vectors that contain elements of independent random variables with 0 mean and single unit variance, we want to investigate what happens with the dot product, which you can either treat like this or like this. This is, I will use this notation. So let's start from the expected value. Some students ask me, okay, also, since these elements of Q are independent and the elements of K are independent, also the covariance, if you like, between Q and K is dependent. This is all to say that we can compute them individually. And this is and this is 0. Do we agree on that? All right. You want to read these? Okay. I will read this part. So let's see what's happening with the variance. I would directly use this formula, which you can find in any textbook of statistics. This is the mean that we computed in the previously. And this is okay. Do we agree on that? Okay, I'm trying to go step by step so that you don't get lost in the process. Some students are very comfortable with math, can already compute it faster than me, probably. So, before I go, because usually students complain, I'm just applying this formula here for this. This is 0. So I will not write again. So this variance is equivalent to this one, which is this one. Do we agree? And the sum, I haven't included it, but it's from 1 to dk, since it's the integral low dimensional representation. And here we have this is all to illustrate that the variance of the dot product is dependent on this decay dimension. And by downscaling with this square root of decay, we avoid this kind of training instabilities. Do we agree on that? Okay. So, any questions before I summarize? So if we kind of try to connect the attention, which is the transformer, the core component of the architecture, with the idiosyncrasies of natural language, I'm trying to kind of bind those together so as to explain you why we have this massive success that previously that highly outperformed all the previous benchmarks on natural language. That we have a distributed and independent representation at each block. So one thing that I haven't said is that since the input and the output is the same, you can stack as many of these blocks as you like. So you can sequentially apply this mathematical operation n times. And with a couple of things in between, you get the transformer block. So the important thing is that at each block, at each multi-head self-attention, we have some distributed and independent representation. So we allow for multiple interpretations and disambiguations of language of the input sentence. Which, as a result, gives us a way to enable the model to depend on the context, both with the positional encodings that slightly alter based on the position of the word, and with these different representations from the heads. And another thing, okay, this is a bit. So number 5 is something that I would like to emphasize. So if we regard the attention matrix, this n by n attention matrix, as some weights, these weights are called data-dependent dynamic weights. Why data-dependent? Because for different input representation, you get a different Q and query, and as a result, a different attention matrix. So they are weights that are created on the fly, online, by the data. And this is massively different than what we have seen so previously from the weights of linear layers and convnets that are slowly updated with backpropagation. Do we agree? Okay. That's why they're called data-dependent dynamic weights. So for different queries and keys, for different input sequences, you get different attention weights. And a last thing is that compared to vision, where you can just resize all the images in a particular dimension, so even though, for example, image that has 1 million images, you can just rescale all the images to 224 or 256 or 512, but you cannot rescale the sentence. You cannot. We have a very high variability in natural language between the sequence length. So one sentence can be one word, like hello, and another sentence, if you read the book from Dostoevsky, for example, can be 100 words or maybe 200 words. So strategies like padding are not so effective. We have a lot of redundancy if we need to pad a sequence from a length of 1 to 200. So the transformer enables you to, all these computations are independent and with the same weights. I removed it, but the weights are not at all dependent on n, which is the sequence length. So we can process any type of sequences, which is nice. And it's highly beneficial for natural language processing and even biological related sequence like proteins, but we will not cover that in this lecture. Okay, so anything you want to discuss about these points? There is one more thing that I will talk about, is the skip connections, which will be in one of the next slides. Any questions so far? Okay. So the last part is more relaxed, no more math for you. So even though this architecture was proposed for natural language translation, we learned as the year went passing by that this is a very general way of making computation and optimizing these weights, this linear projection W, query keys and values. It's a very general computing machine, if you like, that can be optimized very efficiently with backpropagation, and it can be applied in all sorts of fields. Here I have some examples from natural language processing, because the slides are a bit old. But later on, at the moment, Transformer is the one and only multimodal architecture that unifies all the possible domains, as long as you tokenize each domain in different way. So 2 years or 3 years later, they found out that you can even apply a transformer into an audio signal by splitting the audio signal, instead of words that we would have in natural language in a sentence, in patches of whatever fixed length. And the same thing in two-dimensional patches for images. For example, for the 256 by 256 images, to take patches of 16 by 16 or 14 by 14 and create tokens in a, project them and create this. So instead of words living in a d-dimensional space, the model, patches of images or audio signal live in this d-dimensional space, and then you have a transformer where you can unify multimodal representations, for example. This is what all these ChatGPT variations that include text and images look like under the hood. And another thing that is very important and was found out later is that each domain, so somebody who works in audio generation and somebody who works in image segmentation, can use the same tricks and the same strategies from natural language based on the transformer by using the same architecture, while 5 years ago or 6 years ago, each field looked completely independent, so you could never use the architecture designed for audio or time series or natural language or computer vision like resonance. You could never apply this in any other field. So all the tricks that one particular domain had to train these models, for example, bus normalization or the resonant block, you could not apply them in another domain. While with the transformer, as long as you tokenize each domain in a different way, you can have a shared architecture and leverage all the tricks from natural language processing, which is the core application here. So, this is not 100% what's happening. We have a couple of things before and after. So the positional encoding is only applied once in the beginning. This gray rectangle is the transformer block that is repeated multiple times. And it just has a bunch of things happening. So these three arrows represent the queries, the keys and values. We have this, similar to ResNets, we have this identity skip connections. So we are allowing the model to ignore this computation in this particular block. And we have norm, which was the layer normalization operation that I wrote about, which also helps for all this stuff to stabilize the training and the gradients and all this stuff, and is independent of the backside. And the feed forward is just another name for a MLP, this multi-layer perceptron. So two linear layers with ReLU or some activation function, non-linear in between. Another thing is that this multi-layer perceptron has it takes this d-model dimension, and in the first layer it up projects it, it increases to 4 times this d-model dimension. So if d-model is 512 to 2000, and then back to 512, and we have no theoretical justification for that, but this is how all the transformers are implemented nowadays. So as long as you grasp multi-head self-attention, the transformer block is just adding a couple of tricks on top. And since the input and output dimension is the same, we just stack multiple of those layers. I have the letter N. I used it before for the sequence length, so here they use it for the blocks. So they just stack all these blocks sequentially. And in the homework you will do a sentence classification. So you have some transformer blocks, you get this output, and in the end you want to classify this text. So the simplest way to do that, because here we have n times this d-model dimension, so the simplest way to do that is to take an average over all of those representations of the words, just to end up with you remember in image classification, we need to have this output in the same space as the classes. So if the text is, for example, positive or negative, we have two classes. So we average the representations of the output representations of all the words. Here I will make a small connection with the database and language translation. So here you can see the encoder, which is the block, the gray block on the left. It has one output, so one output representation that it kind of goes into the to the decoder block. And as you can see, it goes in one of the three positions for queries, keys, and values. So based on what we have discussed so far, if the input is one language that you want to translate, let's say French or Spanish, and on the right side we have, on the left side we have the language that we will translate the sentence. So let's say English, and on the left English, on the right Spanish, French, whatever. We have these two arrows from the encoder. This works. So these two arrows, do you believe we have queries, keys, and values? What are the database as we discussed before? Is it queries, keys? Which of the two? Queries, keys, and values, yes?
Keys and values.
Yes. Just to be sure that we are in the same context. And the query comes from the language we want to translate, which comes from the right block. And this is what we call cross-attention, which is the same illustration that I had with this colored illustration on the multi-head attention, where you asked me why queries have a different dimension from keys and values. So here keys and values come from the base language, the language we are aiming to translate. And this is what they call cross-attention or attention. And it's different from self-attention. And I have an illustration here. So the encoder's output is the values and the keys, as your colleague said. And the different representations here, there is this paper from Attention is All You Need that proposes architecture. They say that they argue, they don't have any proof about that, but they argue that we can learn different representation, which can be syntactic related representation or semantics. Syntax is how language is written. So there is only one component I haven't referenced, which was in the decoder side. So the left is what we call an encoder, and the right is what we call a decoder. And there is only one difference, that we have masked attention. So we mask the sequence. Maybe I can draw to illustrate the point. So let's say we have this n by n attention matrix. So when we want to translate a sentence, we don't want to provide the target to the model, so we cannot provide the translated sentence to the model during training. So we mask the input before it is visible to the transformer. So here you can see this a bit complicated, but at a certain point, this illustration, where we have these three elements from input vector x. And during this multiplication, we put this minus infinity, which would result after the softmax in zeros in this operation. So the lower triangular part would be zeros, which means that on the first step we are translating the first word. You can also make the same illustration by putting a zero here. So in the first step we have no information on the output, how the sentence will look like in another language. And we predict the first word, then we predict 2 words, then we predict 3 words, and then we predict the whole sentence. So this concept is called autoregressive because we predict the first word in the translated language, and then we need to refeed it in the model's input. So we take the output of the model and we use it as an input in the next stage. So instead of differently from image classification where you just do one-shot classification, you pass the model, here you need to predict, even though during training we don't do that. Let's say during inference we would need to take the output of the model and use it in the next step. And in general this is used for all these decoding architectures, which is the current state-of-the-art models like this ChatGPT you're probably using. And this is essentially implementing by integrating this square matrix M, which has a size of n by n, which has minus infinity in the upper triangular or the lower triangular part. Due to all these these tricks of the architecture, it has been shown that this model is exceptionally good at translating sentences because it learns to swap the order of the words. This is not from a transformer architecture, but a very nice illustration from French to English, where the classic example between English and other Latin languages is that in English we have first the adjective and then the noun. So the black horse, if you like, while in other languages we need to swap to translate this. So in Spanish it would look like the horse black. And these kind of representations can be captured with this kind of attention. Another thing about this n by n attention matrix is that it's not symmetric, and some other preliminary results have been seen during the years. Here I have an illustration to show what do I mean with data dependent dynamic or fast weights. These colors mean that these weights are computed from the attention matrix and are specific to this input sequence, while the black ones, which are the fully connected layers, the linear layers and the convolutional layers, are black, indicating that they are slowly changing with backpropagation. And of course, the big bottleneck of the attention mechanism is the computational time complexity of this attention matrix, which is n squared, and many researchers are working on creating less costly mechanism. And using this decoder, I will end up with this because we're out of time. So the current state of the art is the most ridiculous thing you would imagine. You start with a sentence, one language, let's say English. You mask all the output, and each time you try to predict the next word in the sentence. And then you do that with 200 or 500 GPUs over huge batch sizes, and then you get what they call this state-of-the-art generative pre-training, this ChatGPT model that you're seeing, is as simple as that in objective wise. So I can assure you that back in 2017, nobody would have imagined that such a small thing, using an architecture like a transformer, plus using a decoder architecture and just predicting the next and the next word auto-regressively, would result in such strong models that can solve all these, the current natural language benchmarks. And with that, I will finish the presentation. Thank you.